Okay, so I wanted to pick up now on the second topic here. And I'm going to place the blackboards over there so I don't keep on the back and forth so much. So, on the topic of quantum mechanics with single atoms. I don't think I'll get very deeply into it in a quantitative sense because I want to focus more on optomechanics with atomic ensembles, but still, given that it really set precedent for a lot of this work and it exhibits a lot of the basic features already, and it was done prior, I think it's important to cover. So the starting point from point one was this James Cummings Hamiltonian. And you'll recall that this James Cummings Hamiltonian has the following eigenstructure. So there's a coupling frequency, which we even obtained the value of during the last presentation. Let me just first set it to 0 and trivially write down what the eigenstates of the system are. So the ground state in the system is an atom that's in the internal ground state, and the cavity being empty of all of its photons. And then there'll be a pair of near-degenerate states, which are either the atom in the ground state and there being one photon in the system, where that's the cavity frequency, or the atom being in the excited state and the cavity being empty. So that's the atomic resonance frequency. And as I've drawn it here, the detuning is negative, just because. Okay, and then similarly, there's another set of states up here, separated by the same amount. This would be one where there's either 2 or 1 photons in the cavity. Now we go to a situation where there is coupling between the atomics, between the atom and the cavity, and you know then that you get hybridization between these near-degenerate levels. Right? So these, let's say these energy states now become separated in energy. This one goes up in energy and that one goes down in energy like you'd expect just based on quantum mechanical perturbation theory. And similarly, these guys are going to separate. The separation is going to be larger generally. So let's just solve for this separation. Each of these so the eigenstructure breaks up into these manifolds of near-degenerate states. The manifolds are composed of these 2 states, which are near each other in energy. And the Hamiltonian within this subspace is simple. There's the average energy of the 2 states, and then we have, let's see, I have delta over 2 minus delta over 2. And this is simple to diagonalize. Just square these things. Okay, so let's focus on the shift that we have from the value of these states where G equals 0. Okay, so I just have to look at the difference of these energies where G equals 0 versus not 0. And we get the following. In the case of essentially a resonant system, where which would be defined by the fact that the detuning here is small compared to the coupling string. I have an energy shift of the states, which is going to be plus or minus h bar root n. So you'll notice in this case that the energy splitting is linear with the coupling strength, and the energy splitting is not linear with the photon number, which is to say that we have a cavity which is now nonlinear because the energy to add another photon, or the energy is not just proportional to the photon number. There's a strange dependence on the photon number. It gives us nonlinear optics at the single photon level, which is interesting. But I'll mostly neglect the resonance case. I'll just think more about the off-resonance case. And in this case, I find that if I just Taylor expand this guy up here, I get that the energy shifts are going to be h bar g squared and over delta. This is the detuning between the cavity and the atom. So now I'm going to get back to having a linear cavity system, right? Because the energy now scales, the energy of the system scales with the number of photons in the system, so it's just a cavity with some frequency. And this quantity over here defines the frequency shift of the cavity due to the presence of the atom inside of the cavity. And in the situation that I've drawn over here, you'll identify that this, let's say we're off resonance, so this state is going to be predominantly composed of an atom in the ground state and a photon in the cavity. So this is going to be the cavity-like state. Which is to say it's going to be the state that I can drive by trying to send light into the cavity. And this is going to be the atom-like state. If I want to access this state, I better should send light, find a way to excite the atom directly rather than the cavity. The cavity's not going to encourage this interaction. And previously there had been a question about the strength of coupling when we're detuned, so this answers that question. Why I said there's no change in the coupling strength of detuning, but the energy shifts certainly change. Okay, so the cavity resonances shift given the presence of atoms inside of the cavity. So that tells you that we have a nice instrument to detect atoms. Okay, so the principle is like this. Imagine we start with a cavity where there's no atom inside. So I'm going to think of a situation where I have a cavity, I have an atom, sorry, not necessarily wiggling. I have an atom that's going to fly through the cavity, and I want to detect the atom when it arrives and maybe do something with it. So the experiments are done by sending a probe light in, looking at the probe light at the output by whatever sort of detector you're interested in, and trying to detect that the atom's there. So let's just plot what the cavity transmission is as a function of probe frequency. So we have, let's say, the empty cavity before the atom is entered. And I would see a line shaped like this. And now the atom enters. So what excitation spectrum for the cavity do I expect? Well, in this resonance case, you remember that there were two energy levels that repelled each other. And they're both fairly cavity-like. So they're about half cavity, half atom, because they started off degenerate. So in that case, for a resonant cavity atom situation, the cavity transmission might look something like this. This would be resonant, or with this thing 0. And this is also the transmission I get for weak excitation, which I have to think about because remember the cavity is nonlinear. Ultimately, if I probe the cavity where the cavity is off resonance from the atom, then there's only one cavity-like state. I don't get two. So maybe I'll get a new cavity line that looks like this. So this shift is going to be G, and this shift is going to have the magnitude G squared over delta. So then I understand what are the correct experimental strategies to see an atom, to register an atom inside of the cavity. So I'll, let's say, measure the transmitted power now maybe versus time. And you can imagine if I start with a probe that probes the cavity right on the cavity resonance, it's initially going to be transmitted with high power. And then when this atom drops into the load volume of the cavity, G is non-zero, the power will be extinguished. And then the atom eventually leaves, and it would look something like this. Ultimately, I could have used probe light not at this frequency, but maybe at this frequency, or maybe this frequency, depending on the situation I'm looking at. So the cavity initially doesn't transmit that probe light, and then the atom enters and it transmits. So these blips and dips in the transmitted power were observed in a number of experiments. I call these things transits. And, well, just seeing them was pretty exciting at first. And then people started paying a lot of attention not only to the fact that these transits occur, but also actually what the form of the signal is when this transit is transiting. But even short of that, you have the cavity QD is a lovely atom detector, and I'd say the most impressive experiment that's been done using that capability is an experiment in the Esslinger group, where they dribbled, the atoms that they dribbled in were coming out of a post-condensate or out of a non-condensed cloud. They kind of dribbled an atom laser field through this cavity and detected one by one as the atoms transit the cavities, and they could tell the difference between bunched thermal states and non-bunched coherent states. They could do atom counting statistics. But anyhow, this method of detecting the properties of the atom that goes through the cavity, if you stop and think about it, doesn't just measure the presence of the atom. It also measures, of course, the position of the atom. It measures the position because, as we talked about previously, this coupling strength, G, which is proportional to the electric field inside of the cavity, is a function of position. So if I can say something quantitative about how much the cavity resonances has shifted, then I can tell you something about what electric field the atom is living in, and therefore where it may have lived inside of the cavity. So that was then the start of people thinking about cavity optomechanics with cold atoms. Just have a single atom. So here's like the first experiment that examined this kind of stuff. This is out of Jeff Kimball's lab. And, so in these outgoing transits, the ones that I've drawn in blue, the cavity is initially non-resonant, and then the atom enters, and the transmitted power rises. And it, has some features. There's sort of signals, there's oscillations at a particular frequency, and you can see all sorts of mayhem going on up there as well. So each of these transits shows the life of one atom as it passed through the cavity. So what can you discern from this transit? You come up with a bit of a model for what you think the atom might be doing inside of the cavity, what the forces on the atom might be in terms of forces in the axial direction, the radial direction, and what the angular momentum of the atom might be. It's not a very specific measurement, this transit measurement of the atomic motion. But nevertheless, thinking about things in sort of a model, or modeling transits and matching them with modeling motion and matching it to these signals, they claimed they were able to determine that the atoms underwent these kinds of orbital motions inside of the cavity, single atoms spinning around within the cavity. And in order to make the transits that are observed here match with the motion that they would have predicted for the atoms, they had to admit that the atomic motion must be very heavily influenced by the cavity field itself. Okay, so there's optical forces on the atom. these optical forces come from. So the formal treatments that are were really very insightful. Some of them were done with an atom that encounters a laser beam in free space. Probably the first significant work there was by Gordon and Ashkin. That's a PRA article of 1980. And then people returned to the question of optical forces on atoms, considering the effects of the electromagnetic cavity. And there's a paper by and Bleichner and Rich in 1998 that spelled this out very nicely. And just summarizing what it is that they do, they introduce, in order to say something about the forces on the atoms, they introduce a force operator, which is defined as being the gradient of the Hamiltonian with respect to the atomic position. And the Hamiltonian, if you recall, has the coupling between the atomic dipole and the electric field, and both of these things depend on position. And you churn through this calculation. You have to think about the dynamics of the object. And you can think about taking either average values for the force or measuring fluctuations of the force, determining fluctuations of the force. And it leads to the following picture. The forces on the atoms have two forms. There's one which you would call radiation pressure. So this is proportional to the photon scattering rate by the atom. It depends on the probability of the atom being in its excited state and then emitting photons. It requires electromagnetic fields, it turns out, that have a spatially dependent phase. That's the only way you get radiation pressure forces. So for example, if I have an atom that's sitting in a laser beam coming in one direction, the laser beam has an electric field which goes like e to the I k dot r. And therefore, there's a phase varying in space, and I'm going to get radiation pressure force. It's going to push in that direction. And the second type of force that's identified is the dipole force. The dipole force is simply, you think of the average value of the gradient of this d dot e term. Is a fine way to determine what the average dipole force on the atom is. And so the way to think of the dipole force then is that I have an atom which is polarized by an electric field, and so it has a dipole moment, and the product of these things is proportional to the intensity. Because there's an electric field square now. And so the dipole force is going to be related to gradients of the intensity. Inside of a standing wave mode of light, either in free space or in a cavity, there isn't a radiation pressure force because the electric field is real. It doesn't have a spatially varying phase. But there is a dipole force. So what was going on in these experiments are dipole forces on the atoms, not radiation pressure forces. So that's what the average forces are. There's also force fluctuations that are significant. And there's fluctuations both from the radiation pressure force and the dipole force. So for example, you get fluctuations, temporal fluctuations in the, yeah.
I didn't understand why there's no radiation pressure.
Yeah, radiation pressure requires that there be an imbalance of incident light intensity from different directions. And then if you write down the total electric field, it has a traveling wave character, a net traveling wave character, right? So there's an electric field that goes as e to the ikx. So that then defines to you how you get radiation pressure forces. inside of a cavity where you have equal intensity coming from both directions, for an object placed in the center, there isn't a radiation pressure force. If you have an object that sits right at the boundary, where you now do have an imbalance, I suppose, on the face of the mirror, I guess you should go back and think about it in terms of radiation pressure. But for the situation here with the atoms inside of the cavity, we're talking about dipole forces. So there's fluctuations that come about. So for example, the dipole moment of the atom will fluctuate. Interestingly, the fluctuations you can get large force fluctuations even at locations where the electric field is zero. But so long as the electric field is going through zero. So that was a little bit confusing in those calculations, but it is certainly correct. You get force fluctuations even when you trap an atom at the node of a standing wave. And then you also get fluctuations in the electric field. You have fluctuations in the electric field on one hand because the atom is interacting not only with some kind of laser field, but also with vacuum field, and these things fluctuate. But in addition, and this is what these guys added to the discussion, inside of the cavity, the fluctuations of the electromagnetic field of the cavity themselves become significant, right? Because now we have a finite number of photons in the cavity field, and so there's fluctuations in that photon number. So that's a new feature to the optical force fluctuations that comes about only inside of the cavity. That's first pointed out in this work. Okay. So what are the mechanical effects that people see? So first of all, with these mechanical forces, one thing that comes about is trapping. And that's seen already here, and that's to some degree kind of obvious. You have red detuned light inside of a cavity that's red detuned from the atomic resonance. That forms an optical trap, and the atoms, as long as there's light in the cavity, the atoms are attracted to the positions of highest light intensity. So that's why these atoms in this case are sort of orbiting around, because they're being held transversely by the optical dipole force. The light is most intense at the center of the cavity, and it dies off away from the center of the cavity. A second thing that people have gone ahead and measured in terms of single atoms inside of cavities is the enhanced diffusion from the force fluctuations inside of the cavity. So again, in this early work in 1980, these guys already calculated that you have an atom that's placed in a standing wave of light, but in free space. What's the heating rate just due to force fluctuations on the atom? And they obtain a certain value. And as I was pointing out earlier, they have this interesting result that there's some types of force fluctuations that come about at the high intensity regions. That's due to the radiation pressure force fluctuations. And there's other force fluctuations that come about where the intensity, where the intensity is zero. That's these dipole force fluctuations. And the combination of them is a constant in a standing wave. It doesn't have any spatial variation anymore. And it has a certain value. What these guys are predicting inside of a cavity is that there's an extra source of fluctuations, sort of the spontaneous insertion and spitting out of photons from the inside of the cavity, which gives you a new type of heating and potentially a much enhanced type of heating due to force fluctuations. And these were measured. I guess there was this work by the Berkeley group. That's in a PRL of 1999, which claims to see this enhanced cavity-induced diffusion due to light-atom interactions, coming from light-atom interactions. And the evidence for seeing this enhanced diffusion was pretty indirect. It was the best you could do at the time. Basically, they had an atom sitting inside of the cavity. They turned on probe light, and they saw with what probability the atom would still be there after some time. And they assigned that to a heating rate. So matching that to simulation, they were able to see that indeed there's enhanced diffusion of atoms inside of the residue. And then finally, there have been nice experiments on cavity cooling. So the forces on atoms inside of a cavity trap, and they also heat by diffusive heating, but they can also cool the motion of an atom in the cavity. So I guess we've been hearing about how optomechanics gives you cavity cooling. The picture that was developed for at least describing how single atoms are cooled inside of a cavity was a little bit different. And so here's what Rich proposed as a way of understanding why you get optical cooling. So let's imagine that we have an atom that we can place somewhere along the cavity axis. So from the discussion I gave you, you know that the eigenstructure of the James-Cummings Hamiltonian, or the eigenstates, and their energies vary according to the coupling strength of the atom to the cavity. So let's say at a position here, x equals 0, the atom is maybe maximally coupled to the cavity. And you see that the two eigenstates that describe the first excited state of the system, they're pushed apart from each other by a maximal amount. In contrast, if I move a quarter wavelength away, I go to a position where the electric field is 0, so there's no coupling between the atom and the cavity. And so in this case, the repulsion is taken out, and these are just the bare states, the cavity and the excited cavity and the excited atom state. And so as a function of position, these energies vary periodically. Now you imagine illuminating the cavity with light at this wavelength. Okay? So an atom comes along, it's in the ground state, and it finds itself at this position where all of a sudden the probe field is resonant with the cavity, because the cavity resonance has been shifted down closer to the probe resonance, to the probe frequency. So the atom has some high likelihood of jumping up to the first excited state here. That is, there's a likelihood of there having been a photon inserted into the cavity. And then the atom moves along, but the energy of an atom interacting with the photon changes because the atom is moving. So it feels like it's climbing up this hill to match the energy of the first excited state when the atom is closer to the dark. So now the cavity is off resonance from the probe, so it's unlikely to receive more photons at the input. And at some point, of course, the photon that's left over inside of the cavity will also leave the cavity. And then the atom will decay back down to the ground state. And now it's unlikely to pick up another photon because the cavity is off resonance until it again gets to a point where it can couple up to the first excited state. And if you imagine the life of an atom doing this, it's frustrating, right? So maybe not. But anyhow, it sort of climbs uphill here, losing energy, but it's unlikely to get excited here and then climb downhill because this is a point where the cavity is off resonance. So the atom is always sort of walking uphill. That's what defines Sisyphus cooling. And the idea is that this extracts energy continually from the atomic system. And cavity cooling was observed in a number of experiments. And then in terms of what's the most interesting frontier of single atom optomechanics, I think the most interesting stuff is recent efforts to try to control atoms inside of a cavity using feedback. And so here the idea is that the cavity is a great detector of the atomic dynamics. While it disturbs those atomic dynamics, maybe it's still possible to take the cavity output and using just classical control, influence the atomic dynamics to achieve some kind of desired result. So here's an experiment in that direction by the Berkeley group. And they look at the cavity emission. So here's the atom sitting in the cavity. Anyhow, they look at the cavity emission and they count the rate at which photons are received in their detector. And by processing that photon number, they can figure out whether the atom is likely to be in the center of the cavity, or maybe it's likely to have left the center of the cavity. And the idea is, if it's near the center of the cavity, let's have the optical force inside of the cavity be a weak trap. a strong trap, so that the atom is climbing up a steep hill. And then when the atom appears to be at the edge of the cavity, almost about to leave the cavity, let's make the optical forces be much weaker, so that when the atom returns to the center, it's climbing down a shallow hill. And in doing so, it's always climbing up steeply and going down shallowly, so it will continually lose energy. And the way they, by feedback, sort of temporally adjust the trap curvature along the radial direction in this cavity is by injecting sort of a toroidal-shaped laser beam along the cavity axis. As they do this feedback scheme, it's like a binary feedback. The trap is either steep or shallow, and they just toggle it back and forth based on what the count rate of photons at the output is. This is all done with electronics, which they were nice enough to show a 3D rendering of, because after all, if you want to publish in Nature, you have to render your graphics in 3 dimensions. Even if it adds no content to the figure, it has to be done. So you see they done it dutifully, and they got that. And, okay, so this shows that you indeed are cooling, you're extracting energy constantly from the atomic system. Okay, so that's all I wanted to say about single atom optomechanics. Are there questions? So maybe now move on to many atoms.
Quick question.
Yeah.
How do they achieve the toroidal edge?
Right, so the cavity, the cavity has the TDN00 mode, but also like the 1-1 modes, or 1-0 and 0-1 modes. So they just tuned their blue detuned laser light, blue detuned for the atomic resonance. They tuned it to one of those other transverse modes, and that pushes the atom to the center. So now we go to the situation of having many atoms in the cavity. So the Hamiltonian that describes this situation has a coupling term between the atom and the cavity, which is additive. So each atom can absorb a photon or emit a photon back into the cavity field, and the coupling strength depends on the position of each of the atoms, which I've labeled by the quantity J. What's the, and Hamiltonian with this structure plus after insert the atomic energies and the cavity energies is known as the Tavis-Cummings Hamiltonian. What are the eigenstates like for the Tavis-Cummings Hamiltonian? So I'll return to a formulation like here. And let me just focus on the first excited state manifold so that we don't get too overwhelmed. So in this first excited state manifold, there's n+1 states that are all near each other in energy. Right? I can have a situation where all the atoms are in the ground state, and there's one photon in the cavity. And then I can have all the states where one of the atoms is excited, and all the rest of them are in the ground state, and the cavity is empty. So there's n of these, and there's one of these. So in the subspace, the Hamiltonian looks the following. There's a lot of entries here. There's the energy of the cavity state and all the atomic states are similarly tuned. There's couplings between the cavity and the first atom and the second atom, and so forth, and all these other entries in that matrix are zero. So we can diagonalize this matrix without too much effort, and we obtain the following. So here's the energy of the atom state before we added any interactions with the cavity. And it turns out that there's still going to be n-1 states with exactly the same energy, even though we've added a coupling to the cavity. These are all dark states. And the way these are created is you consider a state which is a superposition of two atoms that are excited, but they're excited, so let's say the ith atom and the jth atom are excited. And if I just divide by the proper values, then you'll find that this is a state that doesn't couple to the cavity. So the coupling from one atom cancels the coupling to the other atom. There's no net dipole moment with which the cavity can interact. Okay. And then there's two states left over. And these are the two dress states that we maybe recall for the single atom cavity 3D situation. And these both are superpositions of either having a photon in the cavity or having a symmetric excitation of the atomic system, i.e. one that's created by